In this video, we will discuss about Weibull distribution. So, Weibull distribution. This is also very important distribution in probability theory. So, we write down about this distribution. This is continuous probability distribution. Continuous probability distribution. And this distribution is also a family of exponential distribution. This distribution was developed by Weibull, which is Swedish physicist in 1939. So this distribution developed by Weibull in 1939. Now, so we write down about the applications. So this distribution has wide applications. First, we write down the applications in reliability engineering and reliability engineering. Second, we have a medical research. Basically, this is very powerful distribution. Third one is quality control. Fourth, finance. And fifth one is climatology. So these are the areas where we mostly use this distribution. So now we move to the uses of this, where we use this distribution. So basically, this distribution is used to calculate time to failure data, time to failure data, such as the probability that a part fails after 1, 2, or more years. So now we explain the probability density function of this distribution. So before explaining this distribution, we write down the parameters. So this distribution described by three parameters. So we know that when we use the exponential distribution, we use one parameter. We use a gamma distribution, we use two parameters. Here we use the three parameters. Three parameters. First parameter we take as a shape parameter. So first parameter, that is the shape parameter. This is denoted by beta. So this is denoted by beta. Second, we use the scale parameter. So this scale parameter we denoted by eta. So this we denoted by eta. And third one is threshold parameter. Threshold parameter. This threshold parameter we denoted by gamma. So this is the symbol gamma, or this threshold parameter is also called the location parameter, or we can say that the location parameter. So these three parameters we use in Weibull distribution. Now, so we already written that this distribution is a continuous probability distribution. Now we write down the probability density function of this distribution. So we write down the let x be a continuous random variable. Continuous random variable is said to have a Weibull distribution Weibull distribution based on three parameters, that is beta, eta, and gamma. So which is defined as fx is equal to beta upon eta x minus gamma upon eta raised to the power beta minus 1 into e raised to the power minus x minus gamma upon eta raised to the power beta. So this is the probability density function of Weibull distribution. So this is depend upon three parameter, that is beta, eta, and gamma. So here we take the values of x. The values of x we write down as when x is positive, greater than equal to 0, beta also greater than 0, eta also greater than 0, and the threshold parameter which lie between minus infinity to plus infinity. So now we defined this distribution for three parameter. So now we write down the thing, that is generally we do not consider threshold parameter. So that means we the threshold parameter is set to 0. Means we take gamma is equal to 0. So when we take gamma equal to 0, so this Weibull distribution convert into two parameters. So this Weibull distribution convert into two parameters. So that is written as fx is equal to beta upon eta. Now, when we put gamma is equal to 0, so this gives us x upon eta raised to the power beta minus 1 into e raised to the power minus x upon eta raised to the power beta. So this is defined for non-negative values only. Non-negative values only. So this distribution basically defined for non-negative values. So that means beta and eta both are positive. Now, so when we put beta is equal to 1, when we put beta equal to 1, so the probability density function of Weibull distribution can be written as fx is equal to 1 upon eta x upon eta raised to the power 1 minus 1 into e raised to the power minus x upon eta raised to the power 1. So this can be written 1 upon eta, or this raised to the power 0 means 1. So into e raised to the power minus x upon eta. So x upon eta. So now we put the value uh, 1 upon eta as, so putting 1 upon eta as lambda. So here we put 1 upon eta equal to lambda. So then we write down this distribution fx is equal to lambda e raised to the power minus lambda x. Lambda e raised to the power minus lambda x. So this is the PDF of exponential distribution. So this is the PDF of exponential distribution. So we uh, write down this as this is the PDF. So this is the PDF of exponential distribution. Now we write down the exponential distribution. Exponential distribution is the special case of both gamma and Weibull distribution. Is the special case of both gamma and Weibull distribution. So there are gamma distribution, gamma distribution that are not Weibull distribution, that means cannot change into Weibull distribution, and vice versa. Okay, so we can convert these distribution gamma and Weibull into exponential, but we cannot convert Weibull into gamma or gamma into Weibull. So we can say that here this is very important. So the family, we can write down, so one family is not a subset of other. One family is not a subset of other. So remember this thing. Now, so when we explain this Weibull distribution, so using graph, so we are drawing the graph so you can understand. So here we take axis, so x-axis and y-axis. So we take the x value and y value, we denote it as fx. This is our origin. So now, because we use 3 parameters here, so we do not use the third one parameter, that is the threshold parameter. So now we are drawing the graph based on 2 parameters. So based on 2 parameters, we are taking as beta and eta. So here we are using 2 parameter beta and eta. So now when we draw the graph, so we just be drawing the graph. So suppose we are drawing the graph in this way. So here we consider the value of beta is equal to 2 and eta is equal to zero point 0.5. So visualization we can see using the R programming or etc. So here we use the beta equal to 2 and eta is equal to 1. Or now when we have this type of shape, so this shape represent here we consider as beta is equal to 1 and eta is equal to 1. So this means the exponential. This is the exponential shape. So these are the shapes when which basically depend upon the values of beta and eta. So now what is the situation when we change the value of beta and eta? That means we take the higher value of beta and lower value of eta. So we draw the another graph. So this is x-axis origin and y, that is function of x. So now here we are changing, that means taking higher values of beta. So this is first graph we take as that means when beta is 10 and eta is equal to 0.5. Similarly, when we take the second graph, so this graph represent here also. So beta we have 10, but eta we have increases as 1. And third one, so third one we have consider as, so here beta we take as constant, that is 10, but eta equal to 2. So this is the third one. So on the basis of parameters, so we have distinct graphs. Okay, so when we are increasing the value of eta and taking the constant value of beta. So now we explain the thing, that means let x be a continuous random variable CRB. So this such that can be written as x follow the Weibull distribution. So x follow, so the Weibull distribution with the parameter beta and eta. So then we are going to obtain the mean and variance. So we are going to obtain the mean. So mean, that is denoted expectation of x, or we can write down as mean mu. So the mean of this distribution, which is eta gamma 1 plus 1 upon beta. So the mean of this Weibull distribution is this. And when we are going to write the variance of this distribution, which is eta square into gamma 1 plus 2 upon beta minus gamma 1 plus 1 upon beta to the whole square. So this is the mean and variance of this distribution, that is the Weibull distribution. So now when we are going to solve the mean of this distribution, so how to calculate the mean or expected value? So we know that the formula of calculating the expectation, which is integration x into fx dx. So here we take x is positive. When x is positive, so then we take limits as from 0 to infinity. So from 0 to infinity, so now we can write down this as integration 0 to infinity x into fx. So what is the fx here? So this we can solve for using two parameter concept. So that means which is beta upon eta up into x upon eta raised to the power beta minus 1 into e raised to the power minus x upon eta raised to the power beta into dx. So we are solving for two parameters. So now when we take as beta upon eta, so beta upon eta, that can be taken from outside the integration. So we take outside the integration. Now we have eta raised to the power beta minus 1 also. So we take eta raised to the power beta minus 1. we take outside. Now we write down the integral in this form x into x raised to the power beta minus 1 into e raised to the power minus x upon eta raised to the power beta into dx. So now we write down one more step here. So this is beta upon. So here we write down eta raised to the power beta. So eta raised to the power beta integral 0 to infinity e raised to the power minus. We write down x upon eta raised to the power beta into x raised to the power beta into dx. So we write down this integral in the form of the gamma function. So now when we are going to solve this, so we have take the help of substitution. So for substitution, so we are putting a let x upon eta is equal to t. So dx upon eta is equal to dt. So when we put the lower limit, so for lower limit here we have the limit of x. So when x is equal to 0, so x equal to 0, so 0 upon eta is equal to t. So this implies that t is equal to 0. So lower limit is remains same. So similarly for upper limit, so here we have x is equal to infinity. So which implies that some infinity upon eta is equal to t. So infinity upon something means infinity. So this gives us implies that t is equal to infinity. So we see that the limit r remains unchanged. So limit r remains unchanged. So we write down the integration. So this is beta upon eta raised to the power beta integration 0 to infinity. This is the integral limit for t e raised to the power minus, this can be written as e raised to the power minus t, t raised to the power beta into x. So what is the x here? So when we calculate the x, so this x gives us x is equal to t eta, x equal to t eta. So this can be written as t into eta raised to the power beta into dx. Dx can be written as eta dt. So this dx eta into dt. So we write down this as beta upon eta raised to the power beta. So here we take eta raised to the power beta plus 1 outside from the integration. So we write down 0 to infinity. So e raised to the power minus t, t raised to the power beta, and this can be written as t raised to the power beta into dt. So t raised to the power beta into dt. So now we take the help of this. So this can be written as beta, and now this can be written as eta integration 0 to infinity e raised to the power minus t beta into t raised to the power beta into dt. Now when we are going to solve this integration, so again we use this, that means t raised to the power beta. We can solve this integration single step. So can be written as equal to y. So t is equal to y raised to the power 1 upon beta. So what is dt? So this dt is equal to 1 upon beta y raised to the power 1 upon beta minus 1 into dy. So what are the limits here? So the limits will be when we put t equal to 0, so 0 y equal to 0, t equal to infinity, y equal to infinity. The limit r remains unchanged. So we can write on beta eta 0 to infinity, and this can be written e raised to the power minus y, e raised to the power minus y into t raised to the power beta we have taken as y, and what is the dt? So dt is equal to 1 upon beta into y raised to the power 1 upon beta minus 1 into dy. So this we can write down as, so beta eta upon beta we take outside, and this gives us a 0 to infinity, and here we write down e raised to the power minus y and y raised to the power 1 upon beta into dy. So now we remember the definition of gamma function. So definition of gamma function definition says that we have gamma n. So what is the value of gamma n? Which is integral 0 to infinity e raised to the power minus x raised to the power n minus 1 into dx. So we write down the power of x in terms of n minus 1. So here we have the power of y is 1 upon beta. But when we write this 1 upon beta in the form of minus 1, so we can write down this as plus 1 and minus 1. So plus 1 and minus 1. So this is our one term. Plus 1 and minus 1. So we can write down this. No issue. So we can write down. So here we use the, so using the definition of gamma function. So here we are using the definition of gamma function. So this gives us eta into gamma 1 upon beta plus 1. So this can be written as eta into gamma 1 plus 1 upon beta. So this is the mean. So here is the answer. So we have already written the what is the mean of this. So mean of this eta gamma 1 plus 1 upon beta. So we have proved this mean of this Weibull distribution, which is which is eta gamma 1 plus 1 upon beta. So similarly, you can calculate the value of expectation of x square. So similarly, you can calculate expectation of x square, which is integration 0 to infinity x square into fx dx. And when we are going to calculate the variance of x, so this will be equal to expectation of x square minus expectation of x to the whole square. So we have already written